Hello and welcome, everyone. Thanks for coming. My name is Shrif Nada. I'm a software engineer at LiveRamp. And so in this talk, we're going to talk about a really cool probabilistic data structure called HyperMinHash that we've been using at LiveRamp. And so we'll basically give a little bit of an overview about what kind of problems we solve at LiveRamp and talk a little bit about some of the counting problems that we've been trying to solve. And we'll see that when you get to a certain scale, like some of the naive or brute force algorithms that we can be using don't really cut it anymore. And so we found some interesting ways to solve these problems via a technique called sketching. So we'll talk a little bit about that. And then we'll also talk about specifically how this HyperMinHash Sketch works under the hood. We won't go too deep into it, but we'll give the basic intuition. And from there, hopefully, you can kind of pick up the pieces from there on your own. And then talk about other use cases where not just how can this be useful in the context of LiveRamp, but also how can this be useful in the broader context of your work as well. So a little bit about me. I work at a company called LiveRamp. LiveRamp is an identity resolution provider. And what that means is LiveRamp basically provides a way for customers to stitch together data from different data sets and address it using the same key space or using a common identifier. And the way that this is helpful is basically it allows customers to use their data on any platform, no matter where it came from. And in a way, it helps empower the open web, especially when it comes to things like advertising and marketing, where currently like the usual suspects hold a lot of the keys, so to speak. And it turns out that when your company's mission is to take any piece of data and make it play really well with any other piece of data, you end up running into some interesting scaling challenges. And so to that end, we operate some Hadoop cluster to the tune of 100 petabytes. Our identity graph has something like 22 trillion edges. And the team where I work, data management, manages about 8 million customer segments. And so we end up seeing some pretty interesting edge cases and pathological kind of cases in how to solve these problems. And specifically, the data management team, very briefly, provides tools for our customers to shape and augment their data sets. So what does that mean? Let's take one example of that. Let's say you're a marketing manager, right? You want to run an advertising campaign. And you have this here for data sets that you're going to use as your building blocks to run a marketing campaign, right? So as you're saying, OK, what kind of marketing campaign should I run? You're evaluating your options. You might ask a certain question like, how many people like cats? Let's say you want to run some pet food advertisement or something like that. You might want to say, how many people like cats or how many people like dogs? You might also ask something a little bit more complicated, like how many people like cats or dogs? You might also ask how many people like cats or dogs and live in Michigan. So the important parts are that you're starting to combine these different data sets in interesting ways now. And then similarly, what if you start with, let's say, a list of people who like cats, and then you want to find people like those. You want to find data sets that are similar to those data sets or segments. How do you go about doing that? Well, on the slide here, we have about 4 data sets. But really, as we said on the couple of slides ago, we have about 8 million of these segments. And the customer could be exposed to any of these segments. So they might want to choose from them at any point during this process, right? So we have like a marketplace where customers can go and buy data from different partners and things like that. So we have millions of these segments. And they range in size from megabytes, tens or hundreds of megabytes, to tens of terabytes. So the way we would answer this question is actually both slow and expensive, right? In the naive sense, if I want to answer this question, I would have to run some sort of job, right? And that job would go and maybe run a join against cat lovers and 25-year-olds to answer whatever question I wanted to ask. And again, as we said, if you have sufficiently large data sets, this question can take minutes, maybe even hours to answer, depending on how complicated the query you want to run is. And it also doesn't sit well with the CFO of the company when we have to pay millions of dollars to run these kind of computations regularly. So, trouble. So to get around this, or actually, I mean, by the time we answer this in the naive sense of the word, marketing manager will have moved on in their life and they'll be interested in different kinds of questions. So how can we answer these questions quickly and inexpensively? And it turns out that there's a really interesting technique called sketching, which is basically when you construct a sketch of a data set, you're creating a data structure that contains only the information you need to answer the questions you care about. So this is a lossy compression. So instead of actually performing your operations on the data structure or the data set, like the cat lovers or the original CSV file that you had, you would just create a proxy data structure that you can use to answer exactly the questions that you care about. And usually this is a lossy compression. So for example, you can't use a sketch to iterate over the original members of a data set or something like that. You do lose information about the data set. But usually this thing is orders of magnitude smaller than your original data set, and so we're happy with that. And to give like a simple example, let's say you have a machine learning classifier that wanted to identify if the picture contains a horse or not. And what you would naively feed to it is just this image of a horse. But you really don't need to kind of give it something so elaborate. You'll see here this has a lot of RGB values. It's fairly high amount of pixels. What you really could give it is something that looks more like this. And if it's a machine learning classifier worth its salt, it should be able to identify, hey, there's actually a horse in there, even though it looks kind of funny. I'm not sure what it is. And you can probably compress this a lot better. You know, this is only black and white. You can probably express it using a few Bezier curves or something like that. You don't actually need a grid of pixels to express this sketch on the right. So wouldn't it be neat if we had, instead of our data sets, sketches that we could use to answer these questions really quickly? Furthermore, it would be really, really neat if these data or sketches were something on the order of megabytes or kilobytes, so that we don't have to run these massive distributed jobs to answer these questions every time we wanted to ask them. Well, the good news is Redis already provides a way for you to answer some of these questions. Who here has heard of PFCount? Show of hands. All right, great. So PFCount already helps you answer these questions. It tells you how big a data set is, and it tells you how big the union of data sets are. The OR there is just, union is just math speak for this OR operation when you say how big this data set, or how many distinct elements can share this property, or that property, or this property. That's just the cardinality of a union of sets. So, okay. Let's step back and think about, okay, what kind of problem are we trying to answer here, really? So mathematically speaking, we're really just trying to ask the size of a set or the cardinality of a set. And there may be duplicates there, right? So you may have the same email show up 3 times or 10 times or however many times. You may ask for the size of the union of 2 data sets. Looks like the pixels or the alignment of the text there is a little off. Apologies for that. So you may ask about the size of the union of 2 data sets. You may ask about the size of the intersection of data sets. And again, all these examples are going to have 2 data sets, but really these questions can be extended to n number of data sets that you care about. And this is the slightly more complicated one, perhaps. How similar are 2 data sets? Remember when we started with a list of people who have a certain property, let's say they like cats, and we want to find people like them in order to advertise to people who look like them. So these are the mathematical queries, or mathematically speaking, this is how we can express the problems we're trying to solve. And again, the naive solutions require O of n memory, require O of n runtime, and they take a really long time and are expensive to run in the worst case. And again, Redis can solve this for you using something called PFCount. So thankfully, not a ton of people raised their hands when I asked about PFCount. So hopefully, you guys will walk away with something, with some new information here. So what we can do here is use this command called PFCount. And it basically, remember the idea of sketching? It uses sketches under the hood. It specifically uses something called the HyperLoglog sketch. And the sketch has some really good properties. So to approximate something, you only need space on the order of log of that thing that you're trying to approximate. So that's pretty huge. It means if you're trying to approximate a data set that has, let's say, 1 billion integers, naive solution would require you to use something like 3.8 gigabytes to do that. Whereas a PFCount sketch, or the sketch underlying PFCount, really only needs 1.5 kilobytes. So already we're starting to see immense space savings here. And the error that you incur with a 99% confidence interval is going to be less than or equal to 2%. And if you remember the marketing manager that we were talking about earlier, they probably are fine if we tell them 1 million people like cats versus 1 million people and 50,000 people. Like, they just want to get a ballpark for the number of people they're going to see or they're going to be reached by this advertising campaign. So let's talk a little bit about what the Hyperloglog sketch is. Again, it's just a probabilistic data structure that can help you estimate the number of distinct elements in a data set, or the number of distinct elements in the union or join of multiple data sets. And so the trick here is we're just gonna, instead of using our original data sets to answer the question, we're just gonna make a Hyperloglog sketch that represents or acts as a proxy for each of our data sets. And then we're gonna use that whenever we wanna ask a question involving the size of the union or the size of a data set. So this is the part of the talk where we're just going to talk a little bit more about what happens actually under the hood. So how do these things actually work under the hood? And we're not going to go too deep into them, but we're going to give an intuition for how this works. And it's helpful in understanding the edge cases, especially when you're thinking about how to use this in your production workloads. So let's take a simpler version of the problem we're trying to solve, right? Assume all of our data is composed of numbers that are randomly sampled. And for any mathematicians in the room, I already apologize. I'm going to use wildly imprecise terms. I'm going to say things like randomly distributed when it's really uniformly randomly distributed. So I apologize in advance. But be it as it may, we're going to have a list of randomly sampled numbers that are in our list. There may be duplicates in there, so you may see the same element 5 times, however many times. And we just want to count the number of distinct elements in this set without using O of n space, ideally. So there's a key observation that powers the Hyperloglog sketch. And when I first learned about this, I really didn't get it. This may seem so out there and so not that useful, but it really powers the entirety of this sketch and entirety of this algorithm. And if you get this idea, it's very easy to build to the rest of the algorithm. So the observation is this. We can very roughly estimate the size of this list of numbers. Again, they're randomly distributed numbers. So we can very roughly estimate the size or order of magnitude of this set by looking at each of its elements, looking at the binary representations of those numbers, and then remembering the largest number of leading zeros that we've seen. So I'll say that one more time. We'll basically look at our list of randomly distributed numbers, look at the binary representation of each element, and then just remember what's the biggest number counting from the left, what's the biggest number of leading zeros that we've seen. Now, why is this a useful thing? This seems like a very esoteric way of counting, right? So to do that, to understand why this is useful, let's think a little bit about some probability that's involved here, right? Remember, our assumptions, which we will relax later, our assumptions are that we have a list of randomly distributed numbers. So if you look at their binary representation, that means that any given bit has a 1/2 chance of being a 0 or being a 1. So the chance that you see no leading zeros in a number, meaning that the first digit in a number is a 1, is just 1/2. That's just the chance that that first digit is 1. The probability that you see a single leading zero is 1/4, because that's just the probability that the first digit is a 0 times the probability that the second digit is a 1. So you start to get, you're getting where this is going to go. If you're seeing 2 leading zeros, the probability that you see that number when you're randomly sampling a number is 1/8, and so on and so forth. Again, why is this useful, right? Well, this is really the key, this is really the kicker here, is we want to answer a question about size, right? We want to know how many things have we looked at. Keeping in mind these probabilities, we expect that we need to look at, for example, two numbers before seeing a number that starts with a 1. Probability is 1/2, so you probably, on average, are going to have to look at two numbers before you see something that starts with 1. And this is the expectation of an event in the geometric distribution, if anyone is interested in that. And again, you expect to have to look at 4 numbers before you see a prefix that has a single leading 0. So probability of seeing a single leading 0 is 1/4. You probably want to look at 4 events or 4 numbers before you can reasonably expect to find something that works there. Again, you have to look at 8 numbers to see something that starts with 2 leading 0s, and so on and so forth. So there we have it. That's actually our first, this is the nucleus of our algorithm. And indeed, this is a terrible algorithm for estimating, but bear with me, we're going to make it better. And this is, for the record, a sketch of size 1. So remember sketching? This is a sketch of size 1, and the only information this sketch contains is just what's the biggest number of leading 0s we've seen. So, OK, how are we going to use this sketch? Well, let's just estimate that the size of the data set we've looked at is 2 to the largest number of leading 0s plus 1. If you remember, this comes from this slide over here, where you expect to have to look at 8 elements before you see something that has 2 leading 0s. So if we see the biggest number of leading 0s we see is 2, let's just guess that the number of things we've looked at is 8. If the biggest number of leading 0s we see is 3, let's guess that the number of elements we've looked at is 16. So basically 2 to the number of leading 0s plus 1. Great. So there's problems with this. I can see some confused looks in the crowd about why on earth are we doing it this way. This is a weird way of counting. Well, we're about to make it better. So here are some problems with this estimation method. It assumes that we have randomly distributed numbers, right? Well, what if I have the user IDs? Those are numbers, but they're probably incremental, like 10, 20, 30, or whatnot. What if I want to count the number of distinct emails in a data set, right? Those aren't even numbers, and they're definitely not randomly distributed. So that's an issue there. We're going to have to get around that somehow. Another problem is estimates are always a power of 2. If you look at this formula here, there's no way you don't get a power of 2. And as much as we like to pretend otherwise, other numbers do exist, and we have to account for those. And unfortunately, the worldly folk that we make products for have to get numbers that aren't just powers of 2. Another problem is that this has a lot of variance, right? It's not crazy if you have a random number generator for you to generate a single number out of that and then find that it has 4 leading 0s or 5 leading 0s, especially if the numbers you're generating are 64 bits. So while this is, the mathematician in me wants to say, technically this is an unbiased estimator, but that doesn't actually count for much in the real world. We have to do something about this variance problem that we have. So let's start by solving this first problem. Let's go to the book of greatest hits in computer science and go to the page that says hashing. So there's this neat thing called hashing, which takes in a random, or not a random, but it just takes in an array of bytes and gives you back an integer. And that integer, if you choose a good hash function, is going to come from a random distribution. So if you have emails, just take the byte representation of that, feed it to your favorite hashing algorithm, Murmur3 or MD5 or whatever. You probably want Murmur3. And then if you take all of the elements in your data set and then hash them, the hash data is effectively randomly distributed. So, well, that was easy. It only took like 30 years of research for us to come up with this. So, so that solves our first problem, really. If you need your numbers to be randomly distributed, well, you need your data to be numbers that are randomly distributed, great, just hash everything that you see. Voila, you have it. So what about the other two problems? Well, we can actually solve these two with the same, with a single swoop, if you will. So let's take a step back and think a little bit about what this estimation method is doing, right? We have some number of elements in a bucket or a box, right? And really the axes here have no meaning or semantic bearing on anything. The axes are just to show you that these are just different elements. Each x is a distinct element, right? And the counting method we've been using thus far is mostly looking at each number in this set or in this bucket, looking at its binary representation, seeing what's the biggest number of leading zeros that we've looked at, right? So we're going to look at each number or each x in this image, and then we're going to say, there it is. That one has the biggest number of leading zeros. So we're going to remember that one. And by doing so, we get, again, a really bad estimate for how many elements are in this bucket, right? Like the size of the bucket, if you will. So this idea is bad in that it doesn't produce really good results consistently. How are we going to fix that? Let's do it over and over again. So what we can do is just arbitrarily partition or arbitrarily just put your elements in different buckets. Instead of taking this big bucket and thinking how big is this single monolithic bucket, say, OK, let's make a bunch of buckets and arbitrarily distribute our elements across those buckets, and then ask, how big is each small bucket in here? And now we can take the average size of a bucket in here. Now, when you take an average between powers of 2, it's no longer a power of 2, so that solves this problem. And then when you take the average size of the small bucket, you can just multiply by the number of buckets, and it'll give you, turns out, a really good estimate of the size of the big bucket. Right? So over here in this picture, we have 12 buckets. So we can just take the size of the bucket on the bottom right, the size of the bucket next to that, the size of the bucket next to that, using our bad estimation method that we had. Take the average of all of those, and then just multiply by 12 to get the size of this larger bucket over here. And that really kind of solves it for us. And bucketing in practice, what does that actually mean? Remember how we hash everything that comes in? Well, just use the first k bits of the hash to determine which bucket something should go in, and then use the rest of the hash to look at the leading zeros. And if this is too in the weeds, forget about it. Just think about this intuitive image. We just take our elements, partition them, and then we run this process multiple times and take the average. So there you have it. I mean, that pretty much solves our 3 big problems that we had with this. And it turns out, like I said, there's a lot of caveats to how we do this in practice. And there's a slide where I'll confess to all the lies that I made and all the imprecise statements that I made. But this is really it. This is the intuition of this algorithm. So you end up with a sketch or a data structure. This is the sketch. Your data structure looks something like this. You just have these buckets, and each bucket contains the largest number of leading zeros you've seen in that bucket. And this is pretty neat. You can build this in a streaming fashion or a batch fashion, however you want. And the way it works is, let's say you have a stream of objects coming in. Let's say these are email addresses, right? What you'll do is that you'll just hash each email address or each object that's coming in. Use the first, in this case, 2 bits to tell you which bucket this is going to go in. And then use the remainder of the hash to look for how many leading zeros are there. And then you're building up this data structure over time. And then at the end, when you want to know how many numbers have I looked at, you'll just take the average of 2 to the value in each bucket, and then multiply by the number of buckets. You can even merge these together. So this is the neat thing. If you remember, this whole thing is to just help us estimate the size of a set or the size of its union with other sets. So you can really just do this process. You can estimate the size of the unions of 2 sets without even having to look at the original data sets anymore. All you have to do is just generate sketches for each data set. And if you want to know how big is the union of 2 data sets, take their sketches and union those. Again, a sketch is a proxy for the data set, so it can just help us answer the questions without having to look at the data set at all. Great. So, and in practice, again, there's a few imprecise statements that I made around here. So this average is not really an average. It's like a harmonic mean. We don't always use this estimation method in practice. It's inaccurate on certain ranges of data. So sometimes we'll use something called linear counting. We always apply like a bias correction. This is just, you know, my slide where I apologize for all the mathematicians in the room. But if you're not interested in that, none of this should matter to you. So the TLDR of this data structure, hyperloglog, I'll also call it HLL in the rest of the slides in case that's confusing to you. Hyperloglog, HLL, same thing. So it's great for estimating a cardinality and union size really quickly because you're basically using a data structure that's 1.5 kilobytes. That's basically a very small set that you can keep in memory. And you can use something of that size to estimate sets on the order of billions of distinct elements with very, very little memory usage. Great, so this helps us answer the top 2 questions that we wanted to ask. Like, remember our marketing manager who was trying to figure out, if I run this marketing campaign, how many people am I going to reach? And if I run that marketing campaign, how many people am I going to reach? Well, we solved 50% of that problem. But there's the second half of this, which is, what about intersections and similarities of data sets? We don't actually have a solution for that because hyperloglog, it turns out in practice, is actually really bad for estimating the size of intersections. It's really fantastic at estimating unions, sizes of data sets, and you can kind of use something called the inclusion-exclusion principle to try to estimate the size of the intersections, but it really doesn't work very well and it's not reliable. So how are we going to solve this? Well, when in doubt, use a sketch. So we're going to use a different kind of sketch called the MinHash Sketch. And the MinHash Sketch estimates something that may seem a little weird at first, but it actually makes a lot of sense when used in conjunction with hyperloglog, the thing we just talked about. And it basically helps you answer all these 4 queries that we just had on the slide before. So what is this MinHash Sketch? So again, it's a data structure that allows memory efficient, accurate and fast estimation of the similarity between data sets. And the similarity, this is technically called the Jacquard index, but colloquially we'll just call it the similarity. The similarity is defined as the size of the intersection of 2 sets divided by the size of their union. Now, why is this a useful thing to compute? Well, this piece is already done for us by hyperloglog, right? So if we compute this similarity estimate, not only can we use it for recommendation, for example, if someone tells me, hey, I have a data set of people that I want to advertise to, I want something that's similar to it. So this can help us with that, but it can also tell me how big the intersection between data sets is by basically, if we use a hyperloglog and a MinHash Sketch in conjunction, MinHash gives us this fraction, hyperloglog gives us the denominator, and then you just multiply those 2 numbers, and you get A intersect B. And again, we're only using 2 sets here just to illustrate, but you can really just do this operation with as many sets as you want. You can have A, B, C, D. I don't know how long the alphabet is these days. So how does this work? Don't worry, this is going to be a lot shorter than hyperloglog because it actually just uses pretty much the same ideas used in the hyperloglog scenario. So let's assume, again, we have 2 lists of numbers which are randomly distributed. Again, not all of our data is going to be randomly distributed, but we're going to assume that that's the case, and we'll hash later. If you got a problem, you can just always hash it out. And we want to estimate the similarity between 2 data sets without using O of n space, ideally. Here's the key observation. Remember how we had a key observation with hyperloglog, which is just look at the number of the biggest number of leading zeros? This is the key observation where that powers MinHash. And if you remember nothing else about how MinHash works, this is the main thing you want to remember. If you have 2 data sets, right? You have data set 1, data set 2, and you want to compare or compute the similarity between those 2 data sets. The way you can do, or one way you can do that, is you can take those 2 data sets, merge them together, right? So just like jumble them all together, and pick an element at random. The probability that that element is in the intersection of those 2 data sets, meaning probability that that element came from both data sets, is exactly the similarity. It's exactly the fraction that we're trying to compute, right? So if you have 10 elements on each side, and there's 5 elements in common, the similarity is just going to be 5 over, in this case, 15, I believe, because the total number of distinct elements is 15, I think. I think I did that math right. So that's the main estimation method that we have to guess at the number of at this similarity number. And take a minute to kind of think about this and convince yourself that this makes sense. And then also, in streaming scenarios, like let's say you're running a web server and you want to build up this data structure or this sketch as you go, you don't actually, for you to choose something uniformly at random, you have to have the entire data set around where you can just choose, or you have to know how big a data set is, and then you can choose an element with the probability 1 over n that it is in your sample. But in a streaming scenario, you don't know how big your data sets are going to be in advance. And so there's actually a way where you can do this just as well without and basically the way you can do that is you can take a sample of the union of those two elements, and then you can take the minimum element of that sample. And it basically works out to be the same thing. Now, what does that actually mean? What does it mean to take a sample? It just means if you hash and take the minimum hash you've seen, it's the same thing as taking, as randomly picking an element from the union of those two data sets. So we have another bad estimator over here. This is another weird sketch that we came up with. So the way we're going to make this sketch is we're going to look at all the elements in those two data sets, and then we're just going to choose one random element, and we're going to ask, does this element exist in the intersection of those two data sets? And if so, we're going to guess that the similarity is 1. And if it doesn't exist in the intersection, we're going to guess that the similarity is 0. Again, as with HyperLoglog, you might ask, why on earth would we do this? This is a really terrible way of guessing the thing that you want to guess. Well, be not afraid. A lot of the issues that are here were also present in HyperLoglog, and we were able to solve those. So how can we fix these issues? Do the same thing that we did in HyperLoglog, just hash everything and then put them in buckets. Do the same experiment a ton of times, and then take the average, and it's going to work out. So the way that this would work is, again, we're getting a stream of elements. We hash this stream of elements, figure out which bucket it's supposed to go into, and then use the remainder of the hash, just keep the minimum hash that we've seen in each of these buckets. So elements are coming into through, let's say bucket 4. We just, in bucket 4, just always run a minimum function on everything that we're looking at. And we do the same thing in all of these buckets. And then how do we use this to approximate similarity? Basically, the way that we do that is we look at pairwise each index. So we look at index 1 in both of these sketches that we have. If those two elements are the same, we add 1 to our count. If they're not, we just don't add anything. And we do that for every index. So we basically go and count the number of equal elements that have equal indices. And then divide that by the total number of elements in the sketches total. And then this has the nice property, the same thing as HyperLoglog, which is you can always merge these sketches together, and you'll get a sketch that represents the union of two data sets. And then if you want to, if you want to know the similarity of that merged sketch, you can always just resort to this formula over here. So the TLDR on this MinHash thing is it basically allows you to quickly and efficiently estimate the similarity between sets. It can be combined with HyperLoglog to approximate the size of intersection. That was that denominator numerator trick that we did over there in the other slide. And it's basically written down over here. If you want to approximate the size of the intersection, make a MinHash sketch and a HyperLoglog sketch. Use the MinHash to get the similarity. Use HyperLoglog to get the size of the union. multiply those two, and you get the intersection. And those right there are all the metrics, or all the queries that we cared about running in that slide that our marketing manager cared about. And I'm sure you're wondering, how accurate is this? How good is this? This is a little less accurate than HyperLoglog. So HyperLoglog was able to give you that number with 2% accuracy. This usually gives you that number with 5% accuracy, depending on how much space you're willing to use for it. But it's still on the order of kilobytes. So you can use something like 64 kilobytes to be able to do all these operations for billions of elements. So what's this? The title of this talk is HyperMinHash. I talked about a HyperLoglog, and I talked about a MinHash. Where does the HyperMinHash come from? HyperMinHash is basically a hybrid data structure. And if you've understood the first two things, then this is a really easy jump. Because if you'll remember, in the MinHash Sketch, we're just keeping the minimum element from each bucket, right? And what is true about the minimum element? It has the biggest number of leading zeros in its binary representation. And so you could actually entirely throw away the HyperLoglog sketch, the first sketch that we made, and just use the MinHash and apply those two algorithms to the MinHash Sketch. It requires a lot more bit level fiddling with stuff, but it ends up that you actually can save a good amount of memory. And so if we go back to our marketing manager over here, he's able to answer all these questions in real time, pretty much in a couple of seconds, because he's now using, instead of the big data sets that could be tens or hundreds of gigabytes large, he's actually just using sketches that are kilobytes, in the range of kilobytes. And we're able to answer these 4 queries really well. And so you might ask, OK, this is great, but I'm not a marketing company. How can I use this thing? Well, wherever you need to answer these queries is an opportunity where you can ask, does it make sense to use something like a sketch, like a HyperLoglog sketch or a HyperMinHash sketch? So there's a ton of applications for this. The simplest application is, for all of these, the answer to it can be business intelligence. You have just a person sitting at a terminal and they're running random queries. But that's a kind of a cop-out use case, because that's a use case for everything. So if you, for example, want to know, how can I use, why is it useful to know the similarity of things? That's useful in natural language processing. So for example, if you're running some natural language processing model, and typically those things are pretty computationally expensive, and so you don't want to, for example, feed it, let's say, duplicate documents, right? Let's say you're scraping documents from the internet. There's a good amount of duplication there, and you want to know how similar are 2 documents. If they're too similar, just give one of them to the NLP model. I don't really get anything out of feeding both of them to the NLP model. It might actually degrade performance. This is useful in genomics. In genomics, a lot of the time, we ask the question, how similar are 2 strains of genes, or something to the tune of that. So that's actually where HyperMinHash came from. The postdoc that came up with HyperMinHash was in genomics, and he needed a fast way to estimate the intersections the similarity between gene sequences. And I think it's pretty cool that it found application in something like marketing, which is fairly different than genomics. But really, the reason for that is that what this boils down to is that it helps you answer these questions really well. And so I'm sure if you take a picture of this or think about this, you'll find somewhere in your infrastructure or in your workloads where you have to answer these questions. And if not you directly, then someone down the hall from you or someone in your company. I'm willing to bet you $1 that that's the case, although no more than $1. There's a fair number of people in the room. And I think that is, one more slide. HyperMinHash is open source. So if you like this and you think this is useful and you say, this is great and all, but how do I use it? You just go to this URL. GitHub has a really neat feature. It's free, called the star feature. So if you go onto that website, just test out the new feature that they have. Yeah, and we also have a Redis module coming soon. I just saw a talk about writing Redis modules in Rust. So I don't know when this will be production ready, but it's coming. It's on the way. And yeah, that's all I have for today. Thank you for your time. All right, so I see we have some questions.
Really good presentation. I'm
Thank you.
doing HackerWare, so algorithm matters a lot.
Yeah.
So I want to ask you, is there any good website you can see a lot of these good algorithms, like from your experience, before we write anything? Check out, hey, MinHash is good, I save you hours of time, right?
Yeah, so
Any good website you can recommend? Yeah.
Yeah, so are you asking, are there good websites where you can learn about this kind of sketching algorithm?
Yeah, like anything will save us time doing a lot of data processing, huge volume like ON, square, ON, log n, those things. Before you write anything, any website you recommend us to check out the algorithm, save us a lot of time before we go do it?
Yeah, so probably the main buzzword you want to look for on Google is probabilistic data structures. There are a few good packages. So Adroll has a really good package on GitHub called StreamSets, I think. Or I forget exactly what it's called, but if you just search Adroll Hyperloglog, you'll find a massive package where they have a ton of really great probabilistic data structures that can help you answer not only this kind of problem, but many other kinds of counting problems. Yeah.
Any intention to do a Python module later in GitHub or only Java? Or?
So there is a Python module for this actually that was written by the postdoc that actually wrote the paper describing this algorithm. So that already exists. You'll probably have to tweak it. It's what I would refer to as research quality code. So you probably want to tweak it a little bit for your production workloads, but the basis is there. Yeah. Any more questions? Oh, we have a question in the back.
Thank you for the talk. You said that the HyperLoglog had a 2% accuracy of error and the MinHash had a 5%. What is the HyperMinHash accuracy of error?
So, I mean, this is kind of a caveated statement because it really depends on how much memory you're willing to give it. So the more memory, so in certain cases, we end up, like in production, in LiveRamp in some cases, we give it like a megabyte or two because we get to certain points and we really, really have to be as accurate as possible. At that level, we basically see 2% error on everything, except in a couple of weird edge cases where basically if the similarity between your data sets is really small, then you start to run into these edge cases where basically the error starts spiraling out of control, but that happens when the similarity is really, really low, like 0.01% similarity. You'll start to see the accuracy of your estimates go totally off the rails. But there are ways to kind of know when that's happening, and in an application environment, you don't actually need it at that level of precision. Usually, you know if it's less than 0.01% similarity, then there's like less than 6,000 people in this segment or something like that. And so you can kind of always get around that, and that's actually what we end up doing. So I guess I didn't answer your question, which is like, what is the accuracy? So at that level of having a sketch that is 4 megabytes large, this is the biggest sketch we've built, a sketch that is 4 megabytes large, when your similarity is less than 0.01%, or above 0.01%, you get accuracy that is, or error that is less than 10%. If you want to do something that is on the order of kilobytes, so if you want to spend 64 kilobytes or 128 kilobytes on this task, you can expect that similarity number to be above, if you would have to have your sets have a similarity above basically 1%. And the less memory you give this, the more this error bound or the thresholds for wacky error starts to rise. But in most of the range of this, you know, if your similarity is anywhere between 1% and 100%, it's always going to be around 5%, no matter how much memory you use. Well, not exactly no matter how much memory you use, but you can be very liberal with using less memory.
Awesome. Thank you again.
Yeah. All right. Looks like that is everyone. Thank you.